So in this video, we're going to look at question 4, question A, in the 2023 paper. So it says this question is about orbits and satellites. There are some useful constants given at the end of the question. In this problem, the orbits of the planets will be assumed to be circular. The home probe, this space probe, was launched on the journey to Mars on the 20th July 2020 with a mass of M0. Of 1,350 kilograms, including 800 kilograms of fuel on board. And then, okay, so the first part of the question asks, so question A1. So it says, at what distance r from the center of the Earth, with r is greater than re, does the gravitational field strength reduces to 1% of the value at the surface? Express this as a fraction of the radius of the Earth. So, well, then I suppose for the gravitational acceleration or field strength, is basically equal to gme over re squared. Now then, in order for this to reduce to 1% of its value, basically divided by 100, then essentially you have to multiply this by 1 over 100. So you basically can see that 100 is basically just 10 squared. So the new radius, that's essentially r. The new radius r should be equal to 10 times re, and that should be the answer to the question. So let's see the second part. So the second part asks, the probe was launched from Tanegashima Space Center in Japan, which lies on the 30-degree latitude above the equatorial plane. Calculate the tangential speed of the space center. Okay, so to calculate tangential speed of the space center, we can do this. So let's say this is the Earth, and then this is the equator, and then 30 degrees somewhere over here. So we can basically just calculate the radius, first of all, the radius of this orbit, and then multiply it by the angular velocity. So first of all, I suppose the radius is basically just equal to re multiplied by cosine theta, which is 30 degrees. And then, so therefore the velocity will be just equal to omega r, which is equal to, omega is equal to 2 pi over the spinning period of the Earth, which is basically 1 day, so therefore it's 24 multiplied by 60 squared, and that is 1 day. Yeah, and then we multiply it by re cosine of 30 degrees, which is root 3 over 2. And then we can calculate this. So re, okay, re, I think it said given constant at the end of the question. Yeah, okay, so over here it says 6.37 10 to the 6 multiplied by cosine 30 degrees. Is that in degrees? Just in case it is not, just say root 3 over 2, and then multiply by, I think that should be okay, so the angular velocity, that's essentially 2 pi over, this should be 24 times 60 squared. Squared. 60 squared. Now that is 401 point, let's say 18 meters per second, and that should be the answer to the question. Okay, now let's see the third part. So the third part says estimate the escape speed of a satellite that is launched from the surface of the Earth with no kinetic energy contribution from Earth's rotation, so that it completely escapes the Earth's gravitational field. So the escape speed, basically, okay, so the idea is this. We have Earth over here, and then we want to escape it, meaning we have to go like infinitely far away from the Earth in order to escape its gravitational field. So let's say infinitely far away. And then, so at this point, in order to minimize the velocity required for the escape speed, the KE is equal to 0 at this point. And then, because it escaped the gravitational field, so therefore the potential energy is equal to 0. Gravitational potential energy. And so, basically what you can say is that the total energy is equal to 0, which is equal to the initial conditions. So first of all is that a half mv squared for the escape velocity, and then we minus the basically plus the gravitational potential energy at that point, which is negative negative gmm mem over re. So then we can cancel out the m because basically we are just dividing 0 by m, and then we rearrange this slightly. So the velocity should be equal to 2 times this, which is essentially 2g me over re inside the square root. So then that should be, so let's say, did it give g? It didn't give the gravitational constant, so just take its value, which is 6.67 10 to the negative 11, multiplied by 2, multiplied by me, which is 5.97 10 to the 24 over re, right? Yeah, okay, so that is 6.37 10 to the 6, and that is okay, so that is 11181 point, let's say 38 meters per second, and that should be the answer to this part of the question. Now let's see the fourth part. So the fourth part says, what is the percentage reduction in energy for a satellite to escape the Earth's gravitational field when launched from the Space Center in Japan, and it is already in a low Earth orbit, so close to the Earth, surface of the Earth. Okay, so, well, I suppose, okay, let's just calculate the first case. In first case, so it has already given a certain kinetic energy because of the tangential speed of the space center, and so okay, so the idea is this percentage reduction in energy for a satellite. Okay, so energy basically meaning the kinetic energy of satellite required. Now for the first part, let's say ES for the space station, then it is basically equal to the kinetic energy required, which is basically a half mv squared, right? Mv escape speed squared minus the initial speed already given, so a half mv squared. The v squared is the tangential speed of the space center, which is let's just say v space center vc squared. Okay, and then the other one is basically just for EO. For let's say just EO for orbiting around the Earth. And then so there are several, I think there's another step we have to consider. So we have a half MVE squared minus the a half mv squared. Now, the v, we can derive mv squared utilizing the centripetal force. So we have mv squared over r, close to the Earth's surface, so let's just say re, is basically equal to the gravitational strength or gravitational force at that point, which is gmm over gmem over r squared. So re squared, yeah. So this should be a half mv squared, so it'll be a half mv squared is basically just gme m over this is re. Okay, so and then the percentage reduction energy. So the percentage reduction, so which one is actually greater? Because it says percentage reduction, then we have to, the initial value is the greater energy. So let's see, let's just calculate the difference between them first. So let's say ES minus EO. ES minus EO is basically ES minus EO is basically just a half GME M over RE plus this is this should be minus a half MVC squared. So okay, and we have to divide this by like the initial value. Let's say E initial. And then, so basically what we can see is that we can cancel out the m, the small m, it doesn't really matter in this case. So, say the numerator should be equal to a half multiplied by, this is 6.67 10 to the negative 11, and then multiplied by the mass of the Earth. I think it's 5.97, yeah, 5.97, 10 to the 24, and then divided by 6.37, 10 to the 6, let me just double check that. Yeah, okay, and then minus, okay, we factor out the half, so we don't need this. So just VC squared, which is 401.18 squared. Okay, now, that is equal to, let's just say 3.12 times 10 to the, this is, 7. So we can see that, okay, so you can see that ES is actually greater than EO, so therefore EI should be equal to ES. So we just divide this by 3.12 times 10 to the 7 divided by the ES, which is equal to, let's just calculate ES for the moment. So ends over, this is a half multiplied by VE squared. VE squared is 11181.38 squared, and then minus VC squared, which is 401.18 squared, and that is equal to, let's just say 50%. Okay, so then this will be the answer to the question. Okay, now let's see the fifth part. So the fifth part over here, it says, okay, so there's a, okay, so more information given in this case, and it says the trajectory of the space probe between Earth and Mars can be represented as part of an elliptical orbit about the Sun. Okay, with the Sun at one focus of the ellipse, shown schematically in figure 10. So that's this diagram over here. And then thus the space probe cruises without the use of propulsion in an elliptical orbit about the Sun to reach its destination. Okay, and then for an elliptical orbit, RV sine of theta is equal to constant, where r is the displacement of the body from one focus, and v is the velocity vector, and theta is the angle between them. Theta is the angle between them, so I suppose the angle between the displacement vector and the velocity vector. Okay, so By considering the influence of the sun only, use the idea of total energy to produce an expression for the velocity of the probe at point P. So, point P near Earth, to produce expression for the velocity of probe at point P, Vp at point A, Va, in terms of gravitational constant, solar mass, and the radius of orbit of Earth, Re0, Reo, and the radius of orbit of Mars, Rno. Okay, so basically what we have to do is calculate the velocity at point P and point A, and essentially we have a kind of like an elliptical orbit, and we want, okay, so we're given the equation RV sine of theta, and this is equal to a constant, so let's just say R1 is equal to constant. Okay, so then R will be constant changing V. Okay, so you want to calculate VP and VA. No, then let's just say in the case of VP, first of all. In the case of VP, it's basically equal to REO VP sine of theta is equal to, because theta in this case is 90 degrees. Yeah, so that should be multiplied by 1 is equal to a constant. Let's just say C, and then in the case of the point at Mars, RMOV VA is equal to C. Okay, so, and then expressions for the velocity, then we want to express these in terms of the gravitational constant, solar mass, and the radius of the orbit of Earth. Well, in this case, we cannot use circular, the equation for circular motion to do this because this is a elliptical orbit. Well, okay. How about this? Let's just say in the instant where the satellite is at P. The instant where the satellite is P, what is happening is that it has a NV squared, VP squared over R EO is equal to G MS M over REO squared. So basically at this very instant, it is undergoing a circular motion. And for that circular motion, this equation must be true. So, okay, so basically based on this, then based on this, what you can do is that cancel out the m's, and then we can do like VP is equal to the square root of GMS over RE. Okay, so basically we don't even need RV sine of theta is equal to constant. We might use that later. So we have, and then we have VA is basically equal to the equivalent for Mars or MO. And that should be the two equations for this question. And then let's see the sixth part. The sixth part says, determine the difference between VA, the Earth's orbital velocity, and the Earth's orbital velocity VE, and the difference between VP and the Mars orbital velocity Vn. Okay, so see over here that VA and VP is actually different. So for this question, this is actually incorrect. But what we can do is that we can move this down over here. I can move this down over here, and then this should be V, VE, and VM. Yeah, V and VM, and then we can use this for this question. Now, let's return to this question. We want to calculate VA and VP. Well, based on this, we can only derive a ratio between them. So because REO VP is basically equal to RMO VA, and it says to express them in terms of the constants. And how do we involve GMMS? Suppose the only way is to analyze the forces or the gravitational potential. Okay, so I think another way to do this is basically using the energy conservation as mentioned in the question. So in terms of energy conservation, we can do this. Let's move this down. So because this might take a bit of space. So in terms of energy conservation, at point P, okay, so at point P, it is basically equal to, the total energy is equal to a half mvp squared, minus, this should be gms m over reo, yeah. And then this is basically equal to a half mva squared minus gm sm over rmo. And then we can cancel out all the m. Okay, and then based on this, you can see this is basically a simultaneous equation, and then we can just substitute it in. So okay, so basically based on this equation, we can get, I think it might be more viable to get VP first. So VA is equal to REO over RMO multiplied by VP. So substituting this in, we get a half VP squared minus, this is GMS over REO is equal to a half this squared. Okay, so that should be REO squared over 2RMO squared multiplied by VP squared, and then minus GMS over, this is RMO. Okay, and then we simplify this. We want to isolate VP. So first of all, move VP to the other side. We get a half minus, this is REO squared over 2RMO squared. VP squared is equal to this plus this, which is, we can multiply that out. So we get GMS. Then we get R, because it's RMO minus REO, yeah. Okay, and then over, this is REO RMO. Okay, and okay, so this is getting more and more complicated. And then what we can do over here is simplify this a bit. If we simplify this a bit on the left side, what we can get is RMO squared minus, this is REO squared, right? Yeah, and then over RMO squared multiplied by VP squared is equal to this. And okay, let's move this down a little. And what we can do is multiply this to the other side, I suppose. We get this VP squared is equal to 2GMS, and then we can cancel out, because this is a difference squared, so we can cancel out that. So what's left on the top would just be 2 GMS and then RMO. Yeah, because the RMO cancels out with this RMO. And then on the bottom what we have is RMO plus REO and multiplied by REO. Right, REO, let me check. So REO, yep, okay, that's correct. So we can get that VP is, I'm not going to write this again. VP is equal to the square root of this entire thing. And then we need to calculate VA. So VA is basically to RE over MO of this entire thing. RE over MO. So that's basically just this flipped. So we have 2 GMS, and then the square root of RMO cancels out with RMO, and we get it on the bottom. So we have RMO over here, and then we have RE over here. Okay, and that will be the answer to this part of the question. So, okay. And then let's move on to the sixth part. So now this will be a lot simpler. So the question, let me see the question again. So determine the difference between, thus calculate the total change in tangential speed needed at point A to allow the probe to cruise its meeting point with, tangential velocity needed at point A to allow the probe to cruise its meeting point with Mars, assuming the probe already has sufficient kinetic energy to escape the gravitational potential well of the Earth. Okay, so technically, velocity needed at point A. Okay, so, technically, the second part of this small question is just wanting us to calculate the difference between VA and VM using the constants. Okay, so let's see. So first of all is VA and VA and difference between VA and the Earth's orbital velocity, and the difference between VP and Mars's orbital velocity. Okay, so first of all, VA and VE. VA and VE. Okay, so VA minus VE, right? VA minus VE. So that's will be a long equation. So what we have over here is VA first of all is 2 times 6.67 minus 11, and then multiplied by the solar mass, which is 1.99 10 to the 30 multiplied by the radius of the orbit of the Earth. So that is 150 10 to the 9. Okay, and then this is over 150 10 to the 9 plus radius of Mars orbit, that's 227 10 to the 9, and then multiplied by 227 10 to the 9, yeah. And then we okay, so I think it might be more conventional for us to just calculate the values first of all, to simplify further calculations. So we have this, and that is equal to okay, 3416.447 meters per second, and then VE is equal to 6.10 to 11 minus 11 multiplied by 1.99 1030. over this is REO, which is 150 10 to the 9. So that is 297.045 meters per second, and then we have VP, yeah, VP. For VP, we have two. Okay, I think it might be better if we just directly just insert. Yeah. Okay, so minus this. We can just edit this equation directly. So the ones that are changing is we flip the position of this and that. Okay. So we have this should be 227 and this should be 150, and that is okay. So 51614.424 meters per second. We also have VA. Wait, this is VM. So we insert which equation? Oh, it's gone. Okay. Just calculate this. So we have 6167 minus 11 multiplied by 9910 to the 30 over this is RMO, which is 227 10 to the 9, and that gives us 24181.126 meters per second. And then we can calculate the differences. So first of all, the difference of VA and VE, right? VA and VE is equal to 34106.447 minus 29747.045. That is 4356.402 per second. And then we also have it says the difference between VP and VM. Okay, VP and VM. VP and VM, that is VP minus VM. That is 51614.424 minus 24181.126. And that gives us 27433.298 meters per second. And this last part says calculate the total change in tangential velocity needed at point A to allow the probe to cruise its meeting point with Mars. Yeah, okay, so the total change in tangential speed, that is basically just VA, right? Yeah, VA minus VM, the total change in tangential speed required. And that is 34106.447 minus this is 24181.126. Okay, now that gives us 9925.321 meters per second. And these are the answers to the question. Okay. Now let's see the seventh. So the seventh part, calculate the speed of a probe on close approach to Mars. It says calculate the speed of the probe on close approach to Mars. Well, the close approach to Mars basically means that at point A, right? So we want to calculate the speed of the probe close to Mars. Then that is, I think, basically just VA, right? Yeah, that's basically just VA. unless I'm missing something. So calculate the speed of probe on close approach to Mars. Does it mean area close approach to Mars? Well, the satellite is orbiting around Earth and Mars. So technically close approach basically means it's at point A. Okay, so basically just VA, right? So the velocity should be equal to VA, which is equal to 34106.447. Yeah, okay, now let's see this last part. Okay, so the last part. On approach to Mars, the speed of the probe must be slow to match the orbital speed of Mars to allow it to be captured in an orbit around the planet. Wait, so it says to match the orbital speed of Mars to allow it to be captured in an orbit around the planet. Wait a sec. It says Mars's orbital velocity Vm. To calculate the total change in tangential velocity needed at point A to allow the probe to cruise to its meeting point with Mars, assuming the probe has sufficient kinetic energy to escape the gravitational potential. We cruise meeting point with Mars. Okay. I feel like I've made a mistake somewhere. Well, the seventh part won't be that easy. Calculate the speed of probe on close approach to Mars. Yeah. I don't think. Yeah, okay. So for the sixth part, it says cruise's meeting point with Mars. Does it mean the difference in the velocity between um VA and the velocity that satellite required to orbit around Mars? So on approach to Mars, the speed of a probe must be slow to match the orbital speed of Mars to allow it to be captured in an orbit around the planet. Well, yeah. Well then, if the sixth part already asks that, then the eighth part won't give this information, I believe. So let's just go on with this. And then this deceleration is achieved by using six thrusters expending half of the foil over 27-minute period, assuming the decelerating force and the rate of the foil consumption K are constants, okay? For the period of time in which the thrusters are in operation, okay? And then sketch a graph the variation of acceleration against time, append appropriate values to the axes. Okay, so assuming the deceleration force and the rate of foil consumption K are constant. So if the decelerating force is constant, then technically the acceleration will be constant because the mass of the satellite is changing. Okay, so let me see. How do we do this? Okay, let's just calculate the acceleration first. Over a 27-minute period. Okay, so over a 27-minute period, half of the foil. So given over here, I believe, yeah, 800 kilograms foil. Now, if it's 800 kilograms foil, then technically, okay, the rate of which foil is ejected is basically just equal to 400 over a 27-minute period, right? Let me double check. So, over a 27-minute period. Okay, so 27 times 60, and that is 400 over 27 times 60. Now that is 0.247 kilograms per second. And then what we want to calculate is I suppose, decelerating force. That will be one of the main variables. So we have the force, and essentially will be dm dt multiply the velocity of which it is ejected. Now, the velocity of which is ejected isn't mentioned in the question. So, assuming the decelerating force and the rate of full consumption K are constants, okay, the decelerating force. Well, if the decelerating force is a constant, then we aren't getting any kind of information, then we can just say it is just a constant. Let's just say f. And then what we want to calculate is simply the acceleration, right? The acceleration in terms of time. So basically over here that should be the constant decelerating force over the initial mass, which is 1350, right? Yeah, 1350 minus 0.247 k. Wait, no, this is not k. This is basically just t. Yeah, t. Yeah. Okay, and this should be the equation. And then let me check the question. So sketch a graph of variation of acceleration against time. Append appropriate values to the axes. Well, if no information is given about the force, then we can't calculate like the specific values for the axes. We can only express them in terms of variables. So I'm not going to use the actual values. I'm just going to say f over mo minus kt. And then, so we basically just graph the function. Also, another point is that we have something like this. Okay, so something like this. This is time, this is the acceleration, and then acceleration is negative because it's decelerating, and then we're starting at some point. Okay, so we're starting at f over mo, which is like somewhere over here. Let's just say f over mo, right? And then as t increases over time, essentially we'll reach a point where kt is equal to mo, and technically just wait, mo. So technically the acceleration is increasing over time. Okay, so let me move this down a bit. So it should be okay, so somewhere over here the acceleration is constantly the magnitude of the acceleration is constantly increasing. So we're starting over here, and then as time goes on, it will increase. Like this. Let me draw this like kind of like this. Wait, let's just make it more exponential. So like this. And then technically, after KT reaches closer and closer to MO, the acceleration will get greater and greater. However, F is negative, so therefore, acceleration will become more and more negative. So yeah. Okay, and then this, yeah. Well, okay, wait a second. Technically over here, MO is basically... Okay, I missed the value over here. The acceleration is this plus. 800. There's an 800 over here. So that is F over M0 plus, say, MF minus KT. Yeah, I feel like I'm missing something over here. So then this should be the same axis, AT, and then it won't be negative as well. However, over time it should be decreasing as well. So it's starting, however, it's from M over MO and plus this is MF, and then it will increase over time. However, it will stop at a certain point and becomes flat. So at this point, that is when all of the foil are ejected. So that should be F over M0, yeah. And the time over here will be just be 2 times 27 minutes. So 2 times 27 minutes, just say 54 minutes. Yeah. Okay, now let's move on. So let's see. So this is the first part of that question, right? You see the second part. The second part over here wanted to calculate an expression for the change in velocity with time. In terms of the total decelerating force, the initial probe mass, the rate of foil consuming K, initial velocity V0, and time t. For the change in velocity with time, change in velocity with time. So we want to calculate the change in velocity with time. Fm0k initial velocity v0 and t. Okay, so wait, m0 is the initial probe mass. Okay, so to not mix the variables, I'm just going to say like this should be mp for m of the probe, the mass of the probe, instead of m0. Okay, so the second part, well, suppose we can start from looking at the acceleration, and then we can integrate it to get the velocity. So the acceleration in terms of time should be equal to F over m0, right? The initial total probe mass minus kt, right? Yeah. Initial probe mass minus kt, and then we have initial velocity v0. Okay, and then we can basically just integrate this. And essentially just integrate this. So this is basically dv over dt is equal to m over mo minus kt, and then we can get basically from v0, and then 1 dv is equal to, this is from 0 to t, f over mo minus kt dt. And then we get, this is supposed to be v minus v0 is equal to, this is minus 1 over k, right? Yeah. So minus 1 over k, minus 1 over k, wait. Then 1 minus m, wait, no. This is f is constant, we get f out. And then we have inside is ln of mo minus kt, and it is from 0 to t. So we get v is basically equal to v0. V0 minus f over k ln of MO minus KT over MO. Okay, now that will be the okay. And then we have VT. Yeah, VT in terms of total decelerating force, blah blah blah. We have all the variables. Okay, that's perfect. However, there's one thing. This is VT, and then where T is T is 0 is smaller than equal to T, and then smaller than or equal to the mass of the foil, which is essentially 800, right? 800 over K, yeah. And then T can be any real number in this range. Okay, that's the answer to the question. Now, let's see the last part. Last part just want us to calculate the force provided by each thruster. Okay, so this is deceleration achieved by using 6 thruster expanding half the foil over 27-minute period. Calculate the force provided by each thruster. Well, okay, so basically in order to calculate the force provided by each thruster, we have to involve F, and then we just divide it by 6. Okay, so then in order to quantify everything, we have to quantify everything. Okay, so we have 800 and K and all that. Okay, let's just do this. Well, what we can do is that when T is equal to 800 over K, when T is equal to 800 over K, the velocity should be equal to 0. Yeah. Okay, so let's just quantify everything. So 0 is equal to V0. Now, V0 is just, wait, no, when that is not 0, it is the orbital speed of the satellite around Mars. So we have to calculate that first. Say VO, now that is basically equal to, let's say, VO squared over R. Wait, it says for the seventh part, calculate speed of probe on close approach to Mars. Okay, I see. So I suppose seventh part is basically just wanting us to calculate that. Okay, let's redo the seventh part, and that should help us with the answer. So for here, technically what we want to calculate is just on close approach to Mars. Now that is mv squared over rm is equal to is equal to g multiplied by m over rm squared. Okay, so v is basically equal to the square root of g and m over, this is rm. Now that is equal to, okay, that is equal to 6.67, and then multiply by, this is the mass of the Mars, which is 6.42, and then 10 to the 23 over the radius of the Mars, which is, okay, so that's exactly the same as Earth. Okay, that's interesting. And then we have 2592.75, yeah, ms minus 1, and this should be the answer to the question. And then we utilize this down over here, so we don't have to do this again. And then we can get is, that is 2592.75. 2592.75 is equal to V0, which is VA, which is 34106.447. Okay, and then minus f over k. So f is unknown, we want to calculate that. K we calculated earlier. That is 0 point something, right? Yeah, 0.247. 0.247, and then ln of this thing. So MO is basically just 1350 plus 800. Now that is 2150 minus KT. It's basically when all foil is expended, we get 800. Wait, is that all the foil or just half of it? Let me check. So, expending half the foil over. Okay, so basically just half of the foil, and then. Okay, so if it's only half of the foil, let's see. If it's only half of the foil, then we just do like 800. We could just get like 400 over. This should be 2150. Yeah, and then for the graph, I think we should also limit it in that region. Okay, so just adjusting this graph slightly. We get it is increasing over time, and then we just stop it over here because it won't get to a constant. It's basically you just stop it over here, and that's essentially 27 minutes. And then this point over here should be MO plus, this is MP over 2. Yeah, because half of it is ejected. Yeah, okay, and then we have this over here. Now, we have all the values, and we can just calculate f. So f is basically just equal to, okay, let me just do everything first. First of all, 34106.447 minus 2592.75. Now that is 31513.697 is equal to, this is a ln of minus 400. That is 1750 over 2150 over 257. Okay, now that is a negative number, which is interesting. Well, okay, let me think. So, yeah, technically the force is just a negative number. Minus this, so therefore the force is simply, just say the magnitude of the force is 31513.697 divided by 0.833. Now that is 37831.569 newtons, and then we divide this by 6. So therefore the force of each thruster is basically 305.26 newtons, and that will be the answer to the question.